Hello, my name is Kenneth Marino. I'm a PhD student at Carnegie Mellon University, and today I'll be talking about our work in incorporating knowledge into computer vision. So the task we're interested in is multi-label classification. Given an image, we want to classify every object and attributes. In this example, we want to classify person, jeans, hoodie, etc. The problem is that these classes are not independent. They're in fact highly dependent because there exists semantic and spatial relationships between all of these categories. So for instance, we know that a person tends to wear jeans. We also have the same relationship between person and hoodie. And we have the on or rides relationship between person and skateboard. So current state-of-the-art approaches to multi-label classification tends to be end-to-end systems. And while these have proven to be extremely powerful, it's more difficult to incorporate knowledge such as graphs into these systems. Previous work in incorporating knowledge has tended not to be trained end-to-end, which has possibly made it less effective. So our goal in this project is to develop an end-to-end system that takes in both the image and a knowledge graph containing the information between all of the different classes and learn a classification for everything. So for instance, in this example, if we knew that jeans and skateboard were in the image, we ought to be able to use our knowledge and reason that there is a person as well. So we want this to have three important requirements. First, it should be efficient, especially for large graphs. Training this efficiently can be a big problem. Second, as we discussed, it should be end-to-end. And we should have some way of interpreting the way that the system uses knowledge. So we build upon gated graph neural networks. You can kind of think about this as a LSTM over a graph. For every node in the graph represents a visual concept like person or horse. And we represent each of these with a hidden state in our model. So at each step, we propagate the information in these hidden states based on the connections in the graph. And we propagate this information differently depending on the type of edge. So for instance, green might be the on relationship and red might be the is relationship. And we learn different transformation functions depending on the edge type. So we do this for some number of steps and mix the information as well as we can. And then we predict an output for every node in the graph. To initialize the nodes, we take the detection scores and we just initialize the hidden states to those. As we mentioned, efficiency is a really important consideration for our problem. Regular GGNN update is actually intractable for large graphs, so we introduce a novel way of expanding the relevant subgraph. And we do this by predicting how important every node might be to the final classification, and we train this network jointly with the rest of our system. So for our experimental evaluation, we evaluate on visual genome and COCO, both in the multi-label classification setting. And for our knowledge graphs, we use the visual genome scene graphs as well as word nets. And our results, we show significant improvement over baseline methods that only use visual features and detection scores. And we also find that we're able to get an intuition into how our knowledge graph is used in our system. So you can find more details about this in our paper, but the basic idea is that we look at the sensitivity of each hidden graph node to a particular output, and this lets us know which nodes and relationships were most important for our classification. Thank you for your time.